Alright guys, let's kick things off with some heavy hitters in the world of generative AI. DALL-E, Clip, VQ, VAE, 2, and ImageGPT. These tools aren't just generating images, they're revolutionizing how we interact with visual content. Imagine you want a picture of a cyberpunk cat riding a unicorn through a neon-drenched Tokyo street at night. DALL-E, with its powerful text-to-image capabilities, can bring that bizarre, beautiful vision to life. It's not just about creating simple objects. DALL-E understands complex scenes, interactions, and even stylistic cues. Show quick clips of various DALL-E-generated images: surreal, realistic, artistic. Now, Clip, that's a different beast. This model learns from massive datasets of images and text descriptions. It's like teaching an AI to actually understand the relationship between language and visuals. This means it can do things like zero-shot image classification, identifying objects in a photo purely based on textual descriptions without needing prior training on that specific task. Picture this. You're building a content moderation system. Clip can help automatically flag inappropriate. DeepMind's creation is focused on generating incredibly high-fidelity, realistic images. Think photorealism, stunning detail, and incredible control over the subtleties. Show amazing examples of VQ, VAE, 2 generated images, hyperrealistic portraits, landscapes. This is crucial for applications in art, animation. Finally, there's ImageGPT. This one's an extension of the impressive GPT-3 architecture, but applied to images. It treats images as sequences of pixels, using the transformer network to generate images or complete partial images based on contextual cues. Show examples of image completion and generation with ImageGPT. Imagine restoring old, damaged photos or creating multiple variations of a single concept. ImageGPT can be invaluable. These 4 models represent a fundamental step forward, each having a unique strength. These really are game changers. Let's move on to a different application of these foundational AI techniques. Now, let's get into something absolutely mind-blowing: the generation of metal-organic frameworks, MOFs, using AI. MOFs are incredible materials with a vast array of potential applications, from gas storage and separation to catalysis. However, creating new MOFs is a challenging endeavor, often involving extensive experimentation. Enter MOFusion, a powerful AI model that uses signed distance functions, SDFs, coupled with a multimodal conditional diffusion model to generate MOF structures. Show 3D models of various MOF structures rotating. But what are SDFs? They're basically a clever way of representing 3D shapes implicitly by measuring the distance from any point in space to the nearest surface. This ensures that the model has a high-level intuition about 3D shape. In this case, the supercell shape. This allows incredible precision in capturing the detailed pore structures of these materials, critical for understanding their properties. MOFusion takes this a step further by adding conditional generation, which is also groundbreaking. You can specify parameters like pore size, void fraction, and even the desired topology using numeric, categorical data, or even text prompts. This lets researchers explore the enormous MOF design space far more efficiently than ever. Show visualizations of conditional generation, different target properties leading to different MOF structures. This is incredibly exciting for materials science. This is not only faster, it unlocks the capacity to design MOFs with precise properties, a concept that was limited to before. It's quite astonishing, really. I feel so optimistic about the potential of AI. What do you guys think? Let me know in the comments. Let's shift gears briefly to talk about the importance of open-source AI. There's a real movement toward making cutting-edge technology accessible to everyone, and OpenELM is a shining example. OpenELM is a state-of-the-art open-source language model, and what makes it truly special is the complete transparency of its development, the release of its entire training framework. Show screen captures of OpenELM's GitHub repository, its documentation, or benchmark results. This is significantly different from big tech companies. They often release only the weights to create an application, but not the training methodology. This is a significant barrier to progress. So, OpenELM allows for comprehensive checks of bias and errors with the model. For any user wishing to contribute to AI's development and progress, this is excellent news. This complete transparency fosters research, collaboration, and trust within the rapidly increasing community of researchers. Imagine the potential for collaborative improvements and extensions, all powered by an open and accessible framework. This also aids in the building of robust language-driven applications. This is truly incredible. What a fantastic achievement. Next, We're stepping into the world of bioinformatics, a field using AI to analyze and even design biological molecules. Generative is a revolutionary tool enabling detailed assessment and humanization of antibodies and nanobodies, which is not easy. Antibodies and nanobodies are protein molecules with incredibly diverse uses in medicine, particularly therapeutic uses. But developing and optimizing these molecules is complex and costly. Show microscopic images of antibodies and nanobodies and structural models. Generative uses a vector quantized variational autoencoder (VQVAE) framework to learn the nativeness of a sequence so that it is quantifiable. This means it can predict how natural a given antibody or nanobody sequence is in the context of a species and also provide an objective, quantitative measure of this nativeness score. Show a graphic illustrating VQVAE architecture and nativeness scoring. This is unbelievably essential because it can help researchers assess the efficacy and safety of antibody candidates, identifying ones that are more likely to perform well and have minimal immunogenicity. But Generative goes even further, assisting in the tedious automation of antibody humanization. It suggests mutations to make non-human antibodies more suitable and compatible for usage in humans, a process that can be challenging and time-consuming. This is incredibly useful for optimizing antibody therapeutics. Show examples of antibody humanization using Generative. It's really a fascinating example of how AI can speed up the process of drug discovery. Let's now look to a completely different use case of generative AI, medical imaging. Accurately modeling brain structures which are complex is key for diagnosing and treating neurological disorders. This is particularly challenging due to inter-patient variability as well as the large size of the datasets. Researchers here created a generative model to synthesize entirely new brain images, preserving realistic morphology, show brain MRI scans, healthy versus diseased. They also showed that their model outperformed state-of-the-art baselines in terms of image fidelity and the maintenance of crucial morphological details. This is determined with different methods: VBM, subcortical volume analysis, and cortical thickness analysis. Show visualizations comparing real and synthetic brain images, highlight preserved morphological features. The resulting model enables the generation of large artificial datasets, which could revolutionize medical imaging and allow for better diagnosis of diseases and improved testing for new drugs. This really shows the power of generative AI in tackling complex real-world problems with far-reaching consequences. It's mind-blowing when one considers the impact this could have on healthcare. What do you guys think? Finally, let's talk about making the latent spaces of generative models more interpretable. These latent spaces are often black boxes, making it difficult to understand why a model produces certain outputs. Space-filling vector quantization, SFVQ. Show a visualization explaining SFVQ. Addresses this. SFVQ is a novel technique involving space-filling curves, which are lines that wind through a space, hitting every point. By incorporating VQ into that, we create ordered codebooks where adjacent codebook elements represent similar features. This is significant because it allows researchers to interpret and explore the latent space, understanding what each point in the latent space is related to. In the case of the voice conversion model, for instance, SFVQ helps in identifying the specific phonetic units each latent vector represents. Show examples of SFVQ-based interpretations of latent spaces. This greater transparency greatly improves on normal VQ. This could improve the process of model development, allowing to make further improvement for the model by targeting specific parts of the latent space. What a wonderful tool. Guys, we've covered a lot today in generative AI. Incredible progress has been made in multiple fields. It is impressive to consider how far we have come in the last few years. We've seen how generative models are not only generating incredible images or MOFs, but also aiding in the process of drug discovery and improving medical imaging. The importance of accessible, open-source models and the need for interpretable latent spaces underscores the collaborative nature of AI development and the necessity for transparent research. We're only just scratching the surface of what's possible with generative AI. The future is bright, and it's full of incredible possibilities. I'm honestly so thrilled and excited about this field, and it's a privilege to share this journey with you. This is a truly exciting time. Thanks for watching, all. Remember to like, subscribe, and don't forget to that notification bell. I'll see you guys in the next video where we will cover something relevant to the audience. Until next time,